So last time we were just introducing the concept of off-shell amplitudes. So an off-shell amplitude is not necessarily an object of physical interest directly. We're more interested in them because they are some kind of crude version of a vertex in the string field theory action. So an off-shell amplitude, I was writing as AGN. It's a map from H hat tensor n into numbers, which satisfies three conditions. One was that that H hat is as big as possible. Two was that the amplitude acting on states which are given by BRST invariant conformal vertex operators is equal to the genus G endpoint amplitude. So in this sense, this AGN is some kind of generalization of an amplitude. And three was that this thing is BRST invariant up to possible contributions from the boundary of moduli space, which we're ignoring. So to develop this concept, or to see what's involved in developing this concept, well, I will focus on the 4-point amplitude on the sphere. E04. So when this object acts on, when it's acting on BRST invariant conformal vertex operators, write it down. It's given by the following familiar expression. It's given by an integral over the complex plane, z wedge dz bar, and then a correlation function on the Riemann sphere, which we can represent as a complex plane. And then now I'm running out of space. So this is the usual expression for the on-shell 4-point amplitude on a sphere. This is a correlation function on the complex plane, and using SL2C invariance, we've inserted three of these vertex operators of these states at their conventional positions. We inserted 1 at 0, 3 at 1, and 4 at infinity. And this leaves the position of one remaining vertex operator, which I've chosen to be phi 2, unfixed, and we have to integrate the position of this operator over the whole complex plane, okay, or over the whole Riemann sphere. And this, and the Riemann sphere in this case is actually identified with the moduli space of genus 0 Riemann surfaces with 4 punctures. Okay? What? Here? It's a B. So let me remind you again that that phi in HQ takes the form C bar V matter of 0, 0, where, okay, again, we're talking about off-shell amplitudes and bosonic string theory. So this guy is weight 1, 1 matter primary in the C equals 26 physical factor of the CFT, and these are the C ghosts in the C equals minus 26 factor. And so implicitly phi 1, phi 3, and phi 4 all have C ghosts, okay? And now this guy doesn't have a C ghost because the C ghost is actually deleted by these B's, B minus 1, B bar minus 1, where B minus 1 is just given by the contour integral of B around the puncture. Okay? And similarly, B bar minus 1. Okay? Any questions? So this is the familiar result in principle. I'm writing. So okay. Okay. So now we can ask about the analog of condition 3 for this amplitude. That is, this amplitude should be BRST invariant. Okay, in particular acting on states in HQ. So that is equivalent to the statement that BRST trivial states decouple. Okay, so we can say, for example, that at phi 1 should be equal to Q of some lambda. Okay, so we can plug that in this expression, and we should find that this thing vanishes up to terms at the boundary of moduli space. So now what you do is you plug this in here. And then you have a contour integral of the BRST current around lambda. And you can pull this contour integral to act on, pull it off this location and have it act on the rest of the stuff in the correlator. So phi 2, phi 3, and phi 4 are BRST invariant because they're at HQ, and the only thing that happens when you act Q on the rest of this stuff is that it acts on the B ghosts. So you find that Q of B minus 1, B bar minus 1, phi 2 of Z bar. This should equal L minus 1, B bar minus 1, phi 2, Z bar, and then minus B minus 1, L bar minus 1, phi 2 of Z and Z bar. Okay, and then you use the OP of the energy momentum tensor with this primary, phi 2, and this gives you B minus 1 bar del phi 2 Z bar minus B minus 1 del bar phi 2 of Z and Z bar. So we've turned the BRST operator into a derivative on the moduli space. Okay? And now, okay, you can just plug this in, and you find that that the amplitude on Q lambda tensor phi 2 tensor phi 3 tensor phi 4, okay, equals, make sure there's no sign, the integral over the complex plane, or I could just say this is the moduli space, okay, of a total derivative, the exterior derivative on the moduli space, acting on okay, lambda 0 0, and then there's this one form piece dz b minus 1 plus dz bar b bar minus 1 acting on phi 2 z bar, and then phi 3 1 1 and phi 4 at infinity. Okay. So now this exterior derivative is acting on this whole thing, and you just this follows from this little computation. And then since this is the integral of a total derivative, it only receives contributions from the boundary of moduli space, which in this case correspond to small circles around the puncture of phi 2, the puncture of phi 3, and the puncture at infinity at phi 4. But we are ignoring these boundary contributions, as explained a couple of times yesterday, and therefore we get that this is equal to 0. Okay?
But when you say that phi belongs to HQ, this means that phi is annihilated by Q, right?
Yes, phi is annihilated by Q. So the HQ are the vector space of BRST invariant conformal vertex operators that you would normally use in computing amplitudes in string theory.
When you say that Q annihilates the vertex operation, it means that you are using the free-field motion, right?
Yeah, from the closed string field theory point of view, yes. So we're assuming that effectively we are assuming that phi satisfies the linearized equations of motion of closed string field theory. So it's the vector space of solutions of the linearized equations of motion of closed string field theory. In fact, it's even a subspace of this vector space, because these operators are not only BRST invariant, but they're conformal in the sense that this thing is a primary operator of weight 0. So it's a representative of the cohomology. You could say it's this is a space of linearized solutions of the closed string field theory equations of motion modulo gauge transformation. So that means it's an on-shell state. So for now, these different points of view might be confusing. So just think of this as an ordinary computation in perturbative string theory, as you would have seen in Polchinski's textbook or something. So normally people don't think about these things as solutions of linearized field equations, but in fact that is what happens in the context of string field theory.
So what can go wrong there in the boundary terms? It's only the OPEs of the I2 with the other field.
Yeah, so what can go wrong is that when you integrate the total derivative, you end up having phi 2 integrated around a small circle around the origin, around phi 3, and also a very big circle at infinity. And of course, if you have operators that are very close on the worldsheet, there can be a divergence from the OPE. But these divergences are functions of the momenta, okay? And you can continue to a kinematic region where they are vanishing, and then analytically argue that they vanish analytically continuing back. So this is a problem associated with using a Euclidean metric on the worldsheet towards the boundary of moduli space. So in principle, in string field theory, you don't have to use this Euclidean metric. You can just, you can define the propagator as 1 over L0, and then such divergences just don't appear. You don't even have to make the analytic continuation.
There is an issue about using Minkowskian metric on worldsheet is that there is no smooth Minkowskian metric on higher genus surfaces.
Yes. So I don't know much about these global problems.
The idea is very simple. If you have Minkowskian, you have colliding, you have interacting strings, then where the string touch, there is a singularity in the metric.
Well, it sounds kind of light cone-ish. I don't know if this is a theorem for any metric that you could impose on. But okay, the implications of that kind of singularity is something that would effectively occur in the interior of the moduli space. And all I'm claiming is that towards the boundary of moduli space, you can use a Minkowski metric, and then you don't encounter these difficulties. But okay, using a fully Lorentzian formalism on the worldsheet over everywhere, I guess it must be possible somehow. I don't know much about the details, but if it's just a question of language in a sense. If the perturbative string theory makes sense, you should be able to describe it in that language as well. But maybe it's awkward. Okay. So this is, so we've looked at the on-shell 4-point amplitude on the sphere. Okay, I just noticed a mistake here. This is A04. Okay, so now we can think about what is involved in taking this amplitude off-shell. So, okay, so for example, we can say that, okay, we take the phi's out of this vector space HQ. So, for example, let's assume that these vertex operators are primaries of weight h bar. Okay, and so such an operator or a state has a simple transformation property under conformal transformations. So if F is some conformal transformation, then you have the following. Okay, we can actually just keep these positions arbitrary. So this is the property of transformation property of the primary under conformal transformations. So we can try to think about what happens if we take. Yes. Okay. You can also. Okay. Oh yes, yes. Oh, okay, okay, of course. Okay. Okay. So, okay, so you can try to plug such an operator into this expression. So you find some difficulty with phi 4, okay? Because if you take phi 4 to be some primary of non-zero conformal weight, then as you push the position of phi 4 out to infinity, then this thing will, then the entire amplitude will have some singular factor given by, is it 2h or z? No. Okay. We'll pick up some singular factor as you push this vertex operator out to infinity. So already we're seeing some problem taking this this expression off shell, but this is easily remedied by fixing the positions of these other vertex operators elsewhere. So we could take phi 1 at z1 and phi 2 at z2, or no, phi 3 at z3, and then phi 4 at z4, okay, where these positions are not at infinity. And then you can write down the analog of this expression, and you can take these vertex operators off shell by considering replacing them with an arbitrary primary operator, okay? So, the difficulty is, okay, well, it's a difficulty, but it's clear that the off-shell continuation of this expression that you generate in that way will depend on the positions of Z1, Z3, and Z4, okay? And the reason is because okay, we can map these positions back to the canonical positions using some SL2C transformation, but because these operators are not acquire a non-trivial factor under conformal transformation, when we try to say map these three operators to a standard position, we will get different answers, okay, depending on where we fix the operators from the beginning. So for any choice of Z1, Z3, and Z4, we generate a different off-shell continuation of the amplitude. And
Could you think of making eventually a feeder definition which is Z1, Z3, and Z4 dependent in such a way you get that inverse?
Yeah, so I will comment on this in a moment. Okay, so, okay, in fact, there's more than a three-parameter ambiguity because we could have chosen some different coordinate systems on the Riemann sphere. So, okay, the complex plane is the conventional and simplest coordinate system, but there are an infinite number of others. And if we had inserted these vertex operators in some other coordinate system and then went off shell, we would have then generated some different off-shell continuation of this amplitude. So what we find, the upshot of this discussion, is that the off-shell continuation of the on-shell amplitude is not unique. Okay.
In a certain sense, this should be obvious because already at the field theory level, we have to fix a gauge and
Yeah, so I'm about to.
what do you get depends on the gauge you fix.
Well, okay, so in fact, I was about to make a related point, which is that is that we should not worry about this. So though the off-shell amplitudes are not unique, they should be this ambiguity at the level of closed string field theory corresponds to your the ambiguity of field redefinition. So so we are free to take our closed string field and generate a new one, okay? And then the off-shell amplitudes computed from the new field will be different from the ones of the old field. So essentially what we're seeing here, that this off-shell ambiguity is really just an artifact of the field redefinition ambiguity that you have in field theory, okay? So in fact, in a generic quantum field theory, off-shell amplitudes are also not unique, okay? But this is not emphasized quite so often because in a usual local quantum field theory, usually you have a preferred choice of field variable. So there's a field which makes the action look as nice as possible in some sense. Or there's a well-defined, so there's a unique choice of field that's established by convention maybe. And once you fix your choice of field variable, or the form of your action, then this ambiguity is fixed. Okay, but presently we don't know the form of closed string field theory, and we don't know how to fix our choice of field variable. So, so this ambiguity in the off-shell continuation will appear until we resolve that question. Any questions about this? Well, this may also depend on gauge fixing, but this ambiguity will also appear, for example, in scalar field theory. Yes, yes. So that's an additional ambiguity that could appear from gauge fixing. Okay, so so as I said, so we have some ambiguity. We shouldn't be surprised or worry too much, but we have to find a nice way of characterizing this ambiguity. Okay. Okay, so the hint, okay, is that, okay, we are looking for off-shell amplitudes of closed string states not vertex operators. Okay, so usually a state and a vertex operator is regarded to be the same thing, but there's actually a subtle difference, which presently is really important for understanding what's going on. So, one way to characterize a state in the CFT is using the oscillator basis. where we say act some creation operators. On the vacuum. Okay, so this is often what one imagines when you're talking about a state. Yes, so I will explain that. So, so I'm saying that these concepts are not quite equivalent, or at least not in the not in the way you would imagine. Okay. So, so when we think about a state in the CFT, usually we're imagining some oscillators acting on the vacuum, okay, rather than a vertex operator. But okay, another representation which is useful for us is the Schrodinger representation. So here we represent a state as a functional of a curve in space-time. Okay, so now we have some curve in space-time, and sigma goes from 0 to 2 pi, and we have some parameterized curve corresponding to x mu of sigma. Okay. So this is somehow the position basis of the state space, where we have some wave functional of a closed string curve in space-time. So it's in fact possible to indicate the dependence on the ghost fields as well by introducing some formal anti-commuting variables into this functional. We don't need to worry about that too much at the moment. So, so let's think about this Schrodinger representation for a minute. So, okay, so given a vertex operator, phi of 0, 0, we can calculate the Schrodinger functional by evaluating a path integral on the unit disk with our vertex operator inserted at the origin. So we evaluate the worldsheet path integral on this unit disk. And then on the unit circle, we have to impose some boundary conditions for the worldsheet fields, which in this case we're assuming are just the free bosons X. So on the boundary of this circle, we impose a boundary condition that the worldsheet scalars should be set equal to this curve that we've chosen in space-time. Okay? So this worldsheet path integral with these boundary conditions defines some functional of this curve x mu of sigma, and this is the Schrodinger functional. So in this way, you could see that given a vertex operator, you can always define a state. Okay, is that clear? So the question is whether given a state, you can always define a vertex operator. Okay. So in some sense, maybe, but
When you say given a state, it means given a Schrodinger wave function.
yes, given a Schrodinger wave functional, or if you prefer, you can work in the oscillator basis and then try to contract with the position eigenstate to recover the Schrodinger functional. And then you can try to find your vertex operator. So it's pretty clear that that in general the notion of vertex operator will be a little bit problematic, at least as you normally think about it. So let me give you two examples. Suppose you consider a path integral on a unit disk with boundary conditions x mu of sigma, okay? But where you displace your vertex operator from the origin, okay? Okay? So this path integral on this disk with this displaced operator will define a Schrodinger functional. So it defines a state. But you see that there's no actual vertex operator on the origin. There's some operator out here, okay? Okay? So you have to, now you could formally say that, okay, we can maybe make some derivative expansion and do some Taylor expansion, right? This is, you know, some translation operator acting on a operator at the origin, and then expand that operator, and then. But okay, you can already see that there's maybe a little difficulty here. Okay, so another example is that you can say consider a path integral on a torus with some hole removed. Okay. Okay. And then on this hole, you can pose boundary conditions x mu of sigma. Okay? So this will also define a Schrodinger functional and therefore a closed string state. Okay? But it's clear in these examples that the notion of vertex operator for these guys is a little bit murky. Okay? So perhaps one can think of some kind of generalized vertex operator. Which is non-local. Yes? Okay, okay. Yes. Okay. So one can consider maybe some kind of non-local vertex operator for these states, but you don't have vertex operators in the way you normally think about in perturbative string theory. So, okay, but what is true, okay, that we can find a basis for the state space using purely local vertex operators. Okay? So that means that in some sense we can write these states in terms of infinite sums of local vertex operators, but the infinite sum itself may not be a local vertex operator in the conventional sense. So, so is this clear? So this is some.
Your practical definition is finite number of oscillators.
Yes, yes. So, yeah. So, for example, a basis could be given by acting a finite number of oscillators on the vacuum state, maybe injected with some momentum, and that would be a basis for the state space, and each element of that basis would be a local vertex operator. Yes, exactly. Yeah, so this is state operator mapping with a little bit of a twist that you can get from the operator to the state, but if you try to go backwards in general, you will not construct an operator that is local in the usual way you were thinking of as vertex operators. That's all I'm saying. So in some sense you could say the state operator map still holds, but with the caveat that your vertex operators really may be non-local objects. Well, this one you could really see it quite explicitly, right? So, so this operator can be written it can be written as some translation of the operator acting on at the origin, right? Okay. 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 So you can write this thing as some kind of translation of the operator at the origin. Now, if you expand this this exponential operator, okay, in a power series in the derivatives, you make some derivative expansion, then the first term will be, of course, phi inserted at the origin, and the second will be some derivative of phi, and and so on. So you could see that this state will be some infinite sum of operators, of local vertex operators, but it itself is not a local vertex operator at the origin. Okay. Well, the reason why we're worrying about this is, because we're, so practically the reason why you worry about it is because, in general, the states that you want to think of in string field theory are themselves non-trivial Riemann surfaces. So this is a good example. So in general, you're trying to glue Riemann surfaces through holes, which effectively define states, but in a more general sense. So phi belongs to H. So HQ will be, I think it will always be local, those operators at the origin.
But it is not in the homology of Q or in the homology of Q bar.
Maybe, so this state is BRC invariant, but I don't think it's an HQ. So first of all, it's ghost number 0. It's not ghost number 2.
Okay, so ghost number 2.
Yes, so you can have BRST invariant states that are outside of HQ, definitely. But in HQ itself, in principle, you could take infinite sums of on-shell states and try to think about whether those would always be local. And that's a question of functional analysis. I'm not really sure. Okay, I don't know useful examples. So from this point of view, we think of a state as really being defined by some kind of disk. And the question is not where do we insert the vertex operators on the Riemann surface, but how do we patch these unit circles onto the Riemann surface. So the question for the off-shell extension is, so an off-shell amplitude requires that you patch disks onto your surface, not mark punctures. Okay. Okay, so returning to the 4-point amplitude off shell. So what we need is, okay, we have 4 states, phi 1, phi 2, phi 3, and phi 4. And each of these states will have their own unit disk, which is parameterized by some local coordinate, which I will call xi1, xi2, xi3, and xi4. So this is called a local coordinate on the unit disk. Local coordinate. And then given these 4 local coordinates on the disks of these states, we need some maps which relate these local coordinates to the surface. Okay, so so if we require that these maps insert the vertex operators at their canonical positions, then we can require or assume that f1 of 0 equals 0, f2 of 0 equals z, and f3 of 0 equals 1, and f4 of 0 equals infinity. So let me draw a picture. So we have our 4 disks. So we have xi1, xi2, xi3, and xi4. Okay, and then these local coordinate maps take these disks into disks in the complex plane. So F1 maps this disk here to a disk around the origin. F2 maps to a disk around the point Z. Okay. And then okay. And then F3 maps to a disk here. And then F4 maps to a disk at infinity. So you could, so a disk at infinity will look like, okay. Okay, now this, I'm afraid this may start looking confusing. Okay, so F4 maps to infinity. Okay, now, okay, the interior of this disk maps here, and the interior of this disk maps here, and the interior of this disk maps here. The interior of this disk maps outside, okay? Okay. So these, okay, so these local coordinate maps will be the data that specifies an off-shell continuation of the 4-point amplitude, okay? So in particular, yes?
When you say that off-shell amplitude require to use disk and not contours, it's really mandatory, or it's just a nice way to characterize this ambiguity as you said before? Because thus you just say that we have this ambiguity, but what you did before, you still adjust contours.
Yes?
And I think that we need the disk to use the local coordinates because it's nice, but is it the only way to do it theoretically?
I mean, are there other ways of parameterizing the off-shell ambiguity? Well, I guess it's not required. So, okay, at the beginning, before getting into this notion, I gave you some other ways of defining off-shell continuation. I'm not quite sure. Probably such continuations could be reformulated in this language, but I'm not quite sure. But this was just, this is one way, okay, a nice way of
I would say that this follows quite directly once you assume that states for you must have that Schrödinger representation, right? So state for you is already a disk, and therefore you have to find, I mean, in an amplitude there should be a function of the states.
Uh-huh.
Therefore, you need these local coordinates to map these disks.
Yes, yes.
Could you not map the disk to points using some conformal transactions? Okay, you would depend on this transformation, but you could always depend on the disk by some points. Which you can deform it.
Some kind of singular conformal map, you're thinking?
I mean, as you do in general when you start with your Riemann surface with like strips and you map it to contours, doing this, but it's, I mean, you want to do kind of the opposite of this transformation. So I'm just asking why we don't work with contours as.
Because I guess you would have to work on the metric. Because
Well, okay.
you take the spike up there and you can put them as an up point because you are performing some wide time distribution of
Okay, so I want to. Okay, let me just finish, and then I will give us a short break. So the proposal is that we should define the off-shell 4-point amplitude should be given by an integral over the moduli space of this correlation of, let's say, dz wedge dz bar of this correlation function on the sphere. So f1 circ phi 1 0 0, f2 circ phi 2 of 0 0, and then f3 circ phi 3 of 0 0, and then f4 circ phi 4 of 0 0, and then with some b ghosts to complete the definition of the measure, which we will describe later. Okay, so this is the proposal for how we should define an off-shell 4-point amplitude. So now maybe I give people a break for 7 minutes or something. And okay, so let's continue. Okay, so we found that okay, that this 4-point amplitude is characterized by four local coordinate maps. Okay. Okay, so we impose some conditions on these local coordinate maps. Okay, so in general, the local coordinate maps F1, F2, F3, and F4 may be functions, okay, of the modulus. Okay, so maybe functions on the moduli space. So in principle, we should really write F1 of xi1 together with z. So these local coordinate maps can depend on xi1, and they can also depend on the point z where we are inserting the second puncture. Okay, so we require that the local coordinate maps vary continuously okay, not necessarily analytically, okay, or holomorphically, with the modulus z. So in principle, so we should write these local coordinate maps. It's a function of the disk coordinate and z and z bar. Okay, so we require that these maps vary continuously, and this is just to avoid some artificial singularities in the integration measure, which might spoil BRST invariance. So what that means is that as we move the puncture or the disk of phi 2, okay, these other disks can also change their shape as we're moving this disk. These disks will also change their shape as a function of z.
Speaking, F1 should depend also on the functionally on F2, F3, because if you don't want them to overlap.
I'm getting to this in a moment. So okay, so we can characterize this data, okay, as follows. Okay, so another characterization. Okay, this is just some language which is often used in this context. So A04 is specified by a section of a fiber bundle is often written as P04. Okay. Okay, so this Okay, so this fiber bundle is the base of this fiber bundle is M04. Okay, and the fiber, the infinite dimensional fiber, okay, parameterizes possible choices of our local coordinate maps. Okay, at some point on the base. Okay. So we can draw a picture. So we have some fiber bundle, okay, whose base is the moduli space of the four-punctured sphere, and whose fibers, okay, parameterize the possible choices of our local coordinate maps. Okay, is this clear? So we're looking for a section of this fiber bundle over the moduli space, which will tell us how to well, I'm just thinking of a fiber as around over some point on M04.
But the Z is not the Z of where you inserted the F2, or
It is. Okay, so the location of the phi2 puncture, okay, is Z. Okay, it's a point on the Riemann sphere, but it's also a point on the moduli space. Okay, so okay. So in particular, so all F1 and F4 can depend on Z and Z bar, okay, but only for F2 does that dependence appear through the position of the puncture. So F1 of 0 will just be 0, independent of Z and Z bar. F3 of 0 will be 1, independent of Z and Z bar. F4 of 0 will be infinity, independent of Z and Z bar. Okay, but still, there's more data in this local coordinate map than just where it maps the puncture. Okay, and this extra data can still depend on Z and Z bar or on the moduli. Okay.
So one of the constraints of that is that they must say that one of 0 is equal to 0 is spin value. Do we have also other constraints?
Yes, so I'm getting to this. So this is so we're looking for a section of this fiber bundle. Okay, and so an admissible section will satisfy two conditions. First, the maps F1 through F4 are 1-to-1. That is, any or 1-to-1 from the disk into the sphere, okay? So that just basically means that, that given any 2 points on this disk, it can't map to the same point on the image, okay? And the reason that you impose this condition is if this point on the image corresponds to 2 points over here, then these points should really be identified, and these points are actually equivalent, and then we're not really working with the unit disk. So this condition is in some sense just a matter of definition. So it's not so important. But the second condition is that the images of the unit disk on the sphere do not overlap. So this condition has already been mentioned a few times in the discussion, but let me, for those who didn't follow, let me explain why you need that these disks are not sitting on top of each other. Okay? So we're looking at some correlation function on the sphere. Okay, so let's just draw the sphere as a sphere. Okay, and then we have some state which is inserted on the sphere through embedding its unit disk in some region on the sphere. Okay. So so we have a unit disk. Okay. Oh, okay. Okay. Let me just put it that way. And then so let's see, how should I? So this is the image of the puncture, and this is the image of the disk, and this is the sphere. So suppose that we want to evaluate this correlation function with a state which is not of the form of a local vertex operator inserted on the disk. Okay. So we want to consider now what happens if we try to evaluate this correlator with a more general state. Okay. So what you are supposed to do is you're supposed to take this little region here on the sphere, and you're supposed to remove it. You're supposed to cut it out. Okay. So that you leave the sphere with a hole in it. Okay. So now we have a sphere with a hole. Okay, so we cut this region out. And now we want to put a more general kind of state in its place. So for example, we could consider this state defined by a path integral over a torus. Okay? Okay? So now what you're supposed to do is you're supposed to take this path integral over the torus, this state, and you're supposed to glue this this hole in the torus to the hole in the sphere, and then evaluate the path integral over the resulting surface. Okay, so this will define basically the contraction of this state with this sphere, and this tells you how to compute the off-shell amplitude with such a state. Okay, is it clear? Okay, so all I wanted to say about this, in motivation of the second condition, is that in order to do this, we have to, in order to glue this state onto the sphere, we have to cut out the unit disk. And if the unit disks overlap, okay, we can't cut out a region of the surface more than once. So if these, if there are two disks on the surface which are overlapping, then there's a problem in this region because we can't, we can only remove that region once. They can touch, actually. Close. I'm sorry. Did I understand your point? So you're wondering whether these disks include the boundary or not? Is that? So if the two disks are at one point. So you're worried about the kind of marginal case where they touch, where you have this kind of picture and they touch. Is that what you're worried about? I think not. Maybe we should. I don't know. But in practice, we don't. So maybe we don't mind if one point is maybe, it's just one point and maybe it gets lost in the lost in the shuffle. But what do you mean?
I mean, if you cut out the two disks, then you get a Riemann surface with boundary that is degenerate.
Yeah. Okay, well, you know well that, for example, in string field theory, if you have the Witten vertex, then these local coordinate maps can actually touch at their boundaries. So, but it is considered slightly more singular than the best case scenario where they're really separated. But so maybe this could be allowed as some kind of marginal case, but I'm not totally sure. Okay, so this condition is important, okay, because we want to be able to define the off-shell amplitude given any four arbitrary closed string states, in particular closed string states which might look like this, okay. Okay.
If you, instead of starting with A04, you start with something with a loop, A14, then the disk should be mapped, the region you cut out should be topologically trivial.
Well, okay, you don't want the images to self-intersect.
Yes, but if you have a handle, you could imagine that you map the boundary of a disk on a trivial cycle.
Can you do such a thing?
I would say, okay. So if you require that they don't, if you require that these maps are one-to-one, then there should be no problem. Okay, up to maybe if you worry about the boundary of the disk, which I'm not worrying about too much, but that the disks shouldn't overlap with themselves, or yeah. So 2 points on the disk should map to 2 points on the sphere and in reverse. Okay, so it seems that, okay, to define our off-shell 4-point amplitude, we need a section of P04, okay. But in fact, since we have to integrate over the entire moduli space, it seems we need a global section, okay. So the question is there a global section of P04? Okay. And the answer is no. Okay. So a priori, it looks like we're running into problems with this idea. Okay. But so let's first explain what the nature of the problem is in choosing a global section of this decorated moduli space. So okay, so let's look at at the unit disk of a puncture phi 2. Okay. So we have the unit disk of the phi 2 state. Okay. And in this unit disk, we can consider a vector field. Okay. Okay. So we could take this vector field to be, say, for some constants, say a and b, a d by d xi 2 plus b d by d xi 2 bar. Okay? So we have a vector field on this disk, and we can just look at this vector field. And then we can map this vector field using okay, so this is a vector field which, okay, this is a vector which I'm placing at the origin. Okay, so we can map this using our local coordinate map into the sphere. So this will give, okay, we can write this as FV, okay. This will give A times dF2 d xi 2 d by dz plus B dF2 bar d xi 2 bar d by dz bar. And this vector will now sit at the point Z. So now we've mapped with F2 into the complex plane. Okay, we have and we have some now vector field which is located at Z. Okay. Okay, so now we can look at this vector field, and you know that this vector field cannot be zero. Okay, and the reason is because these derivatives, df2 d xi2 and df2 bar d xi2 bar, cannot be zero because by definition these maps are one-to-one. Okay, so one-to-one map at the origin cannot have vanishing first derivative. So we know that these coefficients of this vector field are non-vanishing, and in particular, they're non-vanishing for any point z in the moduli space. Okay, so that means that in order to have a global section of P04, we would need to have a globally defined non-vanishing vector field on the sphere. Okay, so this is impossible. Therefore, we have to think about, okay, so therefore we need a section, or we will have to work with a section with some singularities. Okay, yeah, so yeah, so okay. Okay, this is just a some motivation. So let's. I'm not exactly sure how to think about what is happening with this vector field as it's approaching here, because okay, I think one has to maybe think about the topology of this a little bit. Okay, but in some sense, okay, if you regard this vector field as non-vanishing at the punctures, then you will find that okay, when this point approaches the other punctures, say at 0 and 1, then you know that this vector field has to become very short, because this local coordinate map is getting smaller so that it doesn't overlap with the local coordinate maps here and here. But I'm not sure whether one should regard the length of this vector as really going to 0 in some. Okay, it's kind of the boundary of moduli space, but okay. So okay, so that is a. So it seems that we need a section with some singularities. So the established way of dealing with this problem, okay. Okay. So the established resolution of this problem is that we should work only with states that have no sense of direction. On the disk. So that is okay, so if we consider the conformal transformation, xi goes to e to the I theta xi. So this is a conformal transformation which just rotates the unit disk of a state. Then this is, then we assume that we are working with states where which are left invariant under this rotation of the disk. So this is the level matching condition. Okay. So effectively, okay, so what I've argued, okay, so modulo some subtleties of the boundary of moduli space, okay, is that really we should not be working with the entire state space of the CFT for our off-shell amplitudes, but a subspace where we don't have to worry about this kind of difficulty, okay? And this subspace is basically states which are level matched, okay? So it turns out that in closed string field theory, we require an analogous condition for the B ghost, involving the B ghost. And without further motivation, I will just claim that the space of states on which we will attempt to define off-shell amplitudes is characterized, so a state phi is in this H hat where we are trying to define our off-shell amplitudes if it satisfies L0 minus phi equals 0 and B0 minus phi equals 0, or this notation B0 minus is equal to B0 minus B0 bar. Okay, and similarly L0 minus. So this is the level matching condition on our state phi. This is an additional condition, which is, yes?
Can you explain again how you solve this
Well, so for a state in okay, which is level matched, then it doesn't matter if at some points in the moduli space this vector field becomes singular or becomes discontinuous, because this state doesn't actually know anything about this vector, the direction of this vector. So if the direction of this vector has to undergo some singular behavior at a point in the moduli space, then the state won't see it. Okay. So in some sense, with states like this, we don't have this difficulty. The what? Okay. Let me say a little more. Okay. Okay, so maybe this will answer your question. Okay, for states in H hat, we do not need global section of P04. Okay. Okay, for states in H hat, what we need is a global section of what I would call P hat 04. Okay, so P hat 04, okay, is pretty much the same as P04, but we impose an equivalence relation, which is that any pair of choices of the local coordinate maps in the fiber, which differ by a phase rotation of the unit disk, should be regarded as equivalent. So that is, for example, if we choose at some point in the fiber some f1 of xi, okay, this should be regarded as equivalent to f1 of e to the I theta xi. So for states in H hat, these two local coordinate maps are equivalent. Okay, and the claim now is that P hat 04 has global section. Okay, so in this way, okay, we've motivated the appearance of the level matching condition in closed string field theory in terms of some kind of topological problem on the Riemann surface. No? This is the claim. Okay, so at least in this case, I think it's okay. On the sphere, it's probably not a problem. So this is widely assumed to be true. I don't visualize what could be the difficulty. Okay. 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 Now, okay.